Is there somewhere in particular I'm supposed to be standing for the?
Don't worry.
Okay. All right, I'll stand here-ish then, I think. All right, so this is based on a paper that went on archive a few months ago with some collaborators. The thing we all had in common is we were at Untitled Chapter a year or two ago. Ning and Grant are at Berkeley, and Aiden just started at Leuven in Belgium. So this is in the broad category of quantum information and quantum gravity, where the idea is you take something from the holography or quantum gravity community and you try to look at it through the light of quantum information, where often there are some nice results people have established in the context of quantum mechanics in general. So specifically, we were inspired by some of the work that's gone on in the last few years about traversable wormholes in Ncft. So I'll review that, then I'll tell you some of the quantum information material I need. In particular, I'll define this part of the title, I'll tell you what I mean by a quantum channel, and then I'll need two specific mathematical tools, namely channel capacity and entanglement witnesses. Then I'll tell you how we can actually view traversable channels, traversable wormholes as a quantum channel, and then how we can actually use this to say something interesting, and then I'll conclude. But before that, there's no Roman numeral 0, so I can't put that on the outline, but some motivation for this. So very generally, what do we mean when we talk about holography or the holographic program? So there's a precise statement involving supergravity and n equals 4 superganic bills that, of course, Messina told us. This was very fruitful for 20 years. But more generally, I'm thinking of just connecting a problem in CFT or large N gauge theory or strongly coupled field theories, fluid dynamics, chaos, all of that stuff, to problems that have something to do with gravity, specifically gravity in a box or AES gravity. This could be either classical or quantum. And when I say we're connecting things, then there's some problem on one side, some problem on the other side. And on either side, the problem can be easy. It can be tautologically true. It can be easy in quotes, which is, I've written a paper on it, therefore it must be easy. So this can be very hard, but it's tractable. We can say things. Or it can be hard, which means we can define the problem, but we don't know how to do it. Or it can be more or less impossible at this point. We don't even know what an answer would look like. So this classification divides holography into some classes. So we can have an easy problem on both sides, or at least a tractable problem on both sides. And this we call a check of ADS-CFT, or evidence for ADS-CFT, because we can actually calculate on both sides. So in particular, there are a nice set of calculations in two-dimensional CFTs, which are very, very symmetric, and therefore you can hope to do some work with them. And ADS-3, which is itself simple because there is no propagating degree of gravitational degree of freedom in the bulk. You can reduce even to one more dimension down. You talk about SYK and GQ8 along gravity. So there's been a huge amount of work about this in the last 2, maybe more years. But I won't really talk about that at all today. There's the thing that people really started caring about quantum information in this context, which is various entropy area connections, which go back to a classic calculation by Brown and Hanot, which this is a pre-Messina thing, but connecting the entropy of an interval on a two-dimensional CFT to a gravitational quantity. And then in holography itself, there's the Ryutakyanagi formula, which connects the entropy of a region on the boundary to the area of a region in the bulk, which ends on that interval. And then there are various generalizations of this. There's the HRT formula, which extends this to dynamical spacetimes. And then there's FLM formula, which adds the leading whatever in correction. You can think of this as adding some actual quantum fields in the bulk. There's a related set of ideas involving modular Hamiltonian considerations. So roughly speaking, this came out of dissatisfaction with the entropy, or the replica trick way to calculate entropy. So there's a nice way to write the density matrix in terms of modular Hamiltonian. And then there's a whole set of ideas, JLMS, which relates relative entropy in the bulk and the boundary, a whole gravity from entanglement program, which a lot of people at UBC and elsewhere have worked on. My supervisor, Mark Romsdonk, in particular. And then there's a sort of separate thread, but I've also put this in this broad category. This relates to what Waldstein and Susskind did a few years ago with the area equals EPR, where you recognize that you can treat the thermofield double state as a state of entangled black holes, and therefore statements about quantum mechanics should map quite directly to statements about general relativity. And some of the same authors, including myself, did some work on this a few years ago that I'd be happy to talk about, but I won't really mention in this talk. All right, then there's the sort of why we care about holography in the first place, which is when we can do a calculation on one of the sides, and then we can use this to define the answer to something we don't know how to do on the other side. So again, the big example is entanglement entropies in areas. So people have proved various forms of this, but that doesn't mean you can explicitly calculate usually what the entropy is in the CFT. But if you know that you're in a holographic theory, you can use these connections to look at like the space of entropies in holographic states. So this is by Veronica Gubani and Matt Hedrick and a whole set of other people who have talked about the holographic entropy cone, traits on holographic entropies. There's a set of things. Taki Nagi has done some work on this recently with computing various other holographic entropies. So entropy purification is one thing. There's a whole set of other things that I don't really have space to list. And then there's the whole holographic complexity story, where complexity in a field theory is in general something that's very hard to compute. You sort of follow your nose and say, all right, based on some wormhole examples, we know that it's something that should increase linearly at late times, and you look for various things in the bulk that look like this. In particular, the things people tend to consider these days are volume or action, and you say, let's call both of these potential holographic complexities and see what we can derive about these quantities. This goes back at least to a paper by Baldacina, but the idea that because ADS-CFT is manifestly unitary on one side, that means that if you can describe the process of black hole evaporation in ADS-CFT, it has to be unitary. So you can relate this to a statement about the long-time behavior of correlation functions in holographic theories. And again, there's been a lot of work on this, but I won't really talk about it.
This is an example of a situation where it's extremely easy on the CFT side, very hard.
Yes.
In
Yeah,
the bulk
exactly.
side,
That's why I've done this.
Yeah. Regarding complexity, is there a nutshell way of saying what it is, very roughly? I mean, what is complexity in the CFT side?
It's the thing that's dual to these things, is honestly the best answer.
It doesn't help me much.
So
I want you to say.
I have a rant that I won't go on about complexity, but the best you can do is in finite dimensional cases. Our condensed matter friends talk about quantum gates, where you're applying like in discrete steps. You have access to say like a phase flip and things like that you can do on a quantum computer. And then you can relate this complexity to the computer science definition of complexity, which is basically like the shortest program you can write down, which accomplishes something. So when we talk about complexity of a state, you say, if I have some free resource, say the vacuum state or a Bell pair or something, what is the most efficient way to get from that to some other state? And in holography, what we generally care about is the complexity of the Hamiltonian that you actually have in ADS-CFT, but that's hard to calculate, so people usually just use these dual quantities instead. And this is related to the whole idea of tensor networks, which is a nice way of discretizing a field theory and actually saying something concrete about like the ground state of a field theory, which again, I'm not going to talk about all today, but I figured I should mention it as one of this class of things where people have done some tractable calculations on both sides. And then finally, there's when both of the sides are hard. This is the shrug emoji, if you haven't seen it before. you sort of say, all right, we already knew quantum gravity is hard. It's not surprising that there's things we can't calculate on both sides. So in particular, if you go away from a large Ncft, and certainly away from large Ncft, what are the 2 dimensions? There's just sort of not a lot you can say. If you care about back reaction, so instead of like some perturbative state around a vacuum or around a black hole, it's hard. That's sort of related to this here. And then I want to focus on this last point more in the talk, which is the general question of when does holography actually apply? If I have a field theory, when can I say it has a holographic dual? And I would say this is both a question about a given Hamiltonian, or you don't even need to get Hamiltonian, a given Hilbert space, a given quantum system. When is it holographic? And specifically, once I've picked a system, what are the states in that theory that I should describe holographically? So in like ADS-CFT itself, you could say every state in the CFT is dual to some quantum gravity state. But in general, we really only understand it when it describes classical gravity. So that's sort of the states that we say are nice and holographic. All right, so one way to view what we're doing in this paper is we're trying to add another entry in this class of problems here, where we're trying to understand things we know on the gravitational side about traversable wormholes, to understand some things that are hard to understand about quantum channels, and vice versa. So in the traversable wormhole story, which I'll review in a second, there's a tractable Cft calculation you can do, where you take a thermofield double state and you deform it in a very precise manner. And you can relate this to a problem which has been understood at least since the 70s of what happens when you throw a shock wave into a black hole. And there's some recent work in the last few years. Schenker and Stanford talked about throwing shock waves into the AES black holes. And then Gauss-Jafferson and Wall worked out the double trace deformation case, and then Modular and Stanford sort of popularized this and thought about the quantum information of this a little bit. And then on the quantum information side, it's fairly well understood how to write down what we mean by quantum channels, which I'll define in a second, but basically things that connect to Hilbert spaces. So we will be able to use this to actually define the traversable wormhole, but it's hard to quantify certain aspects of this. So in particular, what's called the channel capacity of the quantum channel, which is how I can actually use this to transfer information. But we'll find out that because we have a holographic dual, we'll be able to put a fairly precise bound on this. And then the hope is we'll be able to actually use this to give a sort of quantum information definition of when the state is holographic, which is vague in general, but it's fairly precise in the traversable wormhole case. All right, so now that I've told you why hopefully you should care about what I'm doing, let me actually fill in some of the details. So the traversable wormhole story starts with some basic observations about holography. So in particular, we've known for a long time that above the Hawking-Page transition, if you have thermal ADS, most of the states in thermal ADS with high enough temperature look like black hole microstates, or they're macro states that look like black holes. And we have a nice way to describe a two-sided black hole geometry, so one where there's two asymptotic regions. It's using the thermofield double state. This is the thing such that when you trace out one of the two sides, you get a thermal state on the other side. So this sort of shows up ubiquitously whenever you do quantum field theory in curved spacetime and you have a horizon. So in this case, we're thinking of the horizon as a black hole horizon, but something very similar shows up in de Sitter space or Riddler space where you're tracing out horizons there. And specifically in holography, we know that the bulk description of this thermofield double state is the ADS Schwarzschild geometry. We call it the maximally extended ADS Schwarzschild geometry because, again, there's two asymptotic regions here. So this is the metric in d dimensions for ADS Schwarzschild. You can see that there's the usual black hole Hawking term here, and then there's the ADS term, r squared. I've just filled in the factors of d. If you want to connect to what Schenker and Stanford did, then typically you specialize to 3 dimensions where you don't really have a physical black hole, you have a BTZ black hole. And in crustal coordinates, it looks like this, and this is the Penrose diagram. So we switched to basically light cone coordinates. We've got a U and a V, which are R plus or minus T, essentially. Okay, so this is a wormhole, technically. It's a two-sided black hole or an Einstein-Rosen bridge. It's a thing where there's two asymptotic regions that are disconnected spacetimes, and there's something connecting them. However, it's not actually traversable. Particles can't cross from one exterior to the other. You can see if I, even a light ray, if I just propagate from the horizon, it will always hit the future singularity. It won't actually cross into this region. So to make it traversable, we actually have to move the apparent horizon away from this event horizon. And we can do this by inserting negative energy, for example, with a shock wave. So this is a bit unnatural if all you have is GR, but it turns out that there's a very easy way to do this in the holographic description. Namely, you insert a double trace deformation. So you coordinate, and on the left and the right-hand side at the same time, you insert some operator. And you integrate over some history of doing this, and there's some coupling here. You imagine that this is on for some finite window of time. And if H is positive, then it turns out, how Jefferson Wall calculated, that the total energy falling through the horizon, so that's this TUU at V equals 0, which is the horizon, is negative. Yeah?
Why is T negative on the left side?
Yeah, okay. So this goes back to, I didn't mention anything here, but there's an N bar here. The reason is time, if I want to boost this forward, then time is forward in this direction and backwards in this direction. So the minus T means that I'm inserting it at the same boundary time here, but that's a positive, that's a time advance on one side and a time delay on the other. Okay, so if H is positive, then the apparent horizon moves inward. So I've taken the same diagram here. So the event horizon is teleological. It doesn't change based on what I'm doing. It just, I take the horizon. I take the top and I draw a line at 45 degrees. That's always the event horizon on Penrose diagram. But now I've added this shock that's coming on both sides in yellow. And you can see that the apparent horizon, which is green, in the asymptotic future, it's on the event horizon. But before the shock goes in, it was at it was further out. So once the shock goes in, the location of the apparent horizon shifts inwards. And if you send signals before this time TF, then you can see that this shock means that they can actually propagate, and instead of hitting the future singularity, they actually escape to the other boundary. So depending on the details of my double trace deformation, I open up a finite window through which signals can escape, and it has some width, which I'm calling alpha here.
Well, the physics of what's going on. So time on the left-hand side is running in reverse, right?
If I apply a global boost to the space-time, time on the left goes to the opposite side of time.
Right, so like on the left-hand side, what's the interpretation of the shock?
Right, so I should still think, if I'm an observer on the left-hand side, I still see time going in this direction.
Oh, okay.
It's just the global symmetry of the naturally extended space-time flips the two of them. So you can think of it as like there's a CPT conjugate on this side. Okay, so this is an important diagram to understand. So are there any questions?
Should I think of our universe as having another copy on the other side, or how does this work? You just go into a different universe.
Yeah, so you can imagine a modification of this idea where instead of having a different asymptotic region, it's the same asymptotic region, but it's just far away. This right now is just some ADS Schwarzschild thing, and there's two separate CFTs here that live on two separate boundaries. So I think in this case, you should really think of it as two separate universes. And then I've just introduced a coupling. It's like saying in my lab, I've got two copies of some holographic system, and then I, by hand, correlate them. Well, I've done the correlating here, and then I add some interaction, the double trace deformation, which is acting on both of them simultaneously. But if I hadn't done that, they'd be like disconnected.
So should we be thinking of these things as something that actually physically could exist, or we're just looking at them hypothetically?
Well, so we're already in ADS-CFT and we're in 3 dimensions, so I think for the
How would
context,
they form?
right, yeah. So I think if you want a lab setup where you would do something like this, it would be something like I'm some higher dimensional bulk observer and I have some piece of material which looks like a boundary CFT, which you can basically realize in a lab, at least up to some length scale. It's like some strongly coupled system. And I happen to know, because I'm a super observer, that it has some bulk description. And I have my very delicate quantum manipulating tools which allow me to place 2 of these in superposition with each other. And that would connect up my 2 separate bulks in this way. Yes?
So if I'm an observer sitting on, say, the right CFT,
Yeah.
how would the double trace deformation look like? Because the way you've written, it has an OL as well. So how would I see the OL?
Yeah, so, all right, so let's look at the causal structure of this thing. So the OL, if you're on the right, can only affect things to the future of the shock. So it hits the singularity, so I will never actually see the left shock on the right side. And in fact, the reason you need 2 shocks is only basically from the CFT perspective. It's because I have a double trace deformation. If I'm just in GR and I have some way of generating a negative energy shock on one side, then it will do all the work of opening up the horizon. It's basically just symmetry.
So for all intents and purposes, it just looks like you can insert the.
Yeah, there's a class, right. I don't even need the fact that they're entangled to do the GR analysis. It's just some negative energy thrown in. Okay, great. And so the point here is there's depending on the deformation, there's a quantity of interest here, which is the width of the wormhole, or the width of the window that I can send signals through, which is alpha. And in order to send a signal through, I have to act before some time TF, and this is definitely well before the deformation is applied. So I have to trust, as an observer on one of the boundaries, that this deformation will be applied. But assuming it is, this procedure will work. All right, so how do we actually figure out what this alpha is? Well, this is the stuff that I said goes back to the 70s, to Hooft and Dre. And then Schenker and Stanford did this in ADS. So in the limit that the shell doesn't back react on itself, we just get a shock wave gives a Vijia space-time, and this is an ADS Vijia geometry, where what's happened is if I take all the hats off of things, then this is just the metric I wrote down earlier. But now, at the time the shock hits the origin of the space-time, I get this theta function perturbation here, where instead of having just V, there's some shift by this width alpha. And this width alpha is related to the energy of the shock wave, the mass of the original black hole space-time, the ADS length, and the time at which I threw it in. And this formula, in the limit that the shock is the magnitude of the energy of the shock is small compared to the black hole, this is an exact statement. So this is a precise equality, and then depending on the details of how I turn on and turn off my double trace deformation, I get this order of 1 factor, and it goes as H over L times the exponential factor. So it's linear in the size of H, assuming that like H is like a top hat thing. I turn it on with some strength for some period of time. So it's really this factor that I care about. Everything else is dimensional analysis. All right, so now let me point out a failure mode of this. So again, if I'm some experimenter who's hanging out on one of these 2 sides and trusting that the deformation will turn on, well, I don't actually know what the state of the space-time is. I only have access to one of the 2 sides. So in particular, I can evolve by a phase. And this corresponds to, instead of time evolving forward on the right and backwards on the left, I evolve forward in boundary time. So I get this overall shift here, which is a phase factor. This you can see, because it's just a phase factor, it doesn't change what the reduced density matrix is. It's still a thermal state on both sides, but I've just shifted everything by a phase. So Malvicino and Susskind argued that this thing just describes a different Wheeler-DeWitt patch of the Penrose diagram. So instead of it being centered at t equals 0, I've now done some time advance forward. But because of the symmetries of the space-time, this looks identical to an observer at the boundary. However, it changes the causal structure, and it might change the signal. All right, so here are two different setups. So the previous one is just the same thing as I showed you before, but now I've highlighted the Wheeler-DeWitt patch corresponding to someone at t0. And you can see that a signal goes through to the other space-time. But now, because of the symmetries of the asymptotic right or left, I can keep T0 and TW the same, but I can slide the Penrose diagram up and down. And now I'm describing a different causal patch here, and you can see that if I'm later than TF, then I can't possibly arrange for a signal to be sent earlier than that, and that means that this signal misses the, it will never actually go through and hit the other side. So what this is saying is, if I only have access to one of the boundaries, I sort of have to take a chance. Some of the possible space-times which look like the Schwarzschild, I'll be able to send something through, and some I won't. So there's a nice quantum mechanics interpretation of this. And the quantum mechanics statement, this is a very basic statement, is that entanglement is not an observer. There's no projector onto the set of all entangled states. And the quick way to say this is if I have two product states and I take the superposition of them, in general they'll be entangled. So what that's saying is entanglement is not a property that's preserved under superposition, but of course Hermitian observables, expectation values are preserved under superposition. So this thing is not, that's a typo, this thing is not actually a subspace of the Hilbert space. So in just basic quantum mechanics, this means that if someone hands me a state and asks me to say, tell whether it's entangled or not, I can't possibly do that. It's just impossible. I can check whether it's some particular entangled state, but I can't look at the whole class. So the bulk equivalent of this, where Schwarzschild is now two entangled black holes, I can't actually determine whether a black hole is entangled with another bulk region. So whether there's an actual connected wormhole. Sometimes, even if I'm doing this procedure where I'm sending a signal through, which would tell me, all right, there's definitely a window here because I can receive a signal on the other side. Well, no, sometimes there are space-times where I'll fail to do that, even though they are entangled. So this will not actually tell me generally whether two states are entangled or whether, in fact, I have two unentangled black holes.
All the procedure is local.
Sorry?
What's the bulk procedure? Is this a local operation?
No, this is something I could even do if I'm the super observer in the lab, right? I've got my two possible holographic theories, and someone walks into the lab and either entangles them or doesn't entangle them, and then asks me to tell what they've done, and I can't do that. That's just a basic quantum mechanics fact, and the bulk manifestation of this is the failure of this signal in the all the time. Okay, but nevertheless, if this procedure does succeed, we do know that they are connected, and we can proceed to learn things about the entanglement structure. All right, I need to speed up a little bit. All right, so now I've told you about traversable wormholes. We have the ability to send signals between the two boundaries using a procedure here. Signal through when there's no trace separation. So we like to understand how we can actually use this to transfer information from one side of one of the asymptotic geometries to the other one. And to do this, I need to tell you a little bit about quantum channels. So why were quantum channels first introduced in the first place? If you're a tabletop quantum mechanics experimenter, you care about dissipative interactions. You have an environment which is messing up your nice superpositions, for example. There's a whole set of interactions which will take a system of interest and some initial state with respect to the environment, and they'll change the entanglement structure, or they'll transfer information between the subsystems. So that means it's not just a map between states, it's a map between density matrices. And all a quantum channel is it's a thing I can do to a density matrix to get another density matrix out. So I've got two Hilbert spaces. I define a set of linear operators on them, which is what density matrices live in. And a linear operator is a good quantum channel when it gives me these properties. So I start with a Hermitian operator, I end with a Hermitian operator. I preserve the trace. So if I have density matrix, that's trace one to start with. After I've applied the div, it better have trace one to end with. And this property of complete positivity. So not only is this a nice operator, but it's still a nice operator if I've added some qubits that I'm not doing anything to. But intuitively, all this definition is saying is it's a map between density matrices and density matrices. All right, so the way you can tell you're doing information theory is you've got an Alice and a Bob at the top. So we think of these Hilbert spaces A and B as the degrees of freedom that are accessible to two experimentalists. Classically, we understand basically everything about this problem. Shannon already worked out how classical communication works between Alice and Bob, and it tells us that how to best exploit a communication channel depends on how many bits you have to send, and it also depends on what Alice and Bob have agreed on what the language they're going to signal in. Are they using Morse code? Are they just sending one bit of information, which is, the British are coming by land, the British are coming by sea, that sort of thing. So there's an information capacity, and this is a function of the channel, and it's also a function of how Alice and Bob have communicated with each other beforehand. So we want the quantum analogy of this, and roughly speaking, this is how many qubits do I have to send through the channel in order to get a certain number of, if I send a certain number of qubits through the channel, how much information, how much entanglement between bell pairs can I extract from this? And I just said that this thing you should expect to depend on the resources available to Alice and Bob. So for example, have they already pre-shared a bunch of bell pairs, which is the sort of thing you need to do with quantum teleportation, for example. So in very general terms, the way we deal with density matrices and quantum channels, which are ugly, is we purify everything in the system, take all of my density matrices and purify them into states. And then I can understand things as unitary maps. So if I've got a density matrix in A, I purify it with some auxiliary system R, and then similarly, I purify B by adding another environment if I need to. And so this is saying, now I can think of this map between a row A and row B as some unitary applied to A and my auxiliary system R, which maps it to some state of B and E, and I've still got my auxiliary system.
It's probably very elementary. But how do I know that I can do that? How do I know I can purify a density matrix?
So assuming I have a good density matrix, well, I already showed you a way to purify a density matrix in general, which is the Romefield double state. So, if I have a thermal density matrix, this is a way to purify it, and I can do a similar thing with an arbitrary density matrix. So, in general, if you give me as big an auxiliary system as my system of interest to start with, I can always do this. And of course, this might not be where there are lots of ways, there are many possible purifications, but with a R, which is at least as large as A, I can always do this to a pure state. And you can just do dimension counting, like look at the number of entries in the density matrix and compare that to the number of free parameters in the state. To get an idea of that. Okay, so I've said I do this verification by adding these two systems. So if the channel is actually moving information from A to B, that means that the that R, after I've applied the channel, R had better be more correlated with B than with just the environment itself. Some of the information in A actually made it to B. So I can define a property called the Coherent Information, which has this form. It's the difference between the entanglement entropy of B by itself with the entanglement entropy of B and R combined. And if this thing is positive, that means that B actually is more correlated with R than the environment. So if I apply the channel once, I should get, if I apply the channel once with this initial state, then this is the amount of information that's been transmitted. So now, more abstractly, what's the best I can do with this channel? Well, I should just take the supremum of this with respect to all possible initial states. So this is called the one-shot channel capacity. And similarly, if I want the asymptotic thing, if I do this a bunch of times, how well can I do? I just allow myself to have n copies of the channel, so I duplicate this, all of my things. Instead of A, I've got n copies of A, so A to the n, and so on with RB. So the problem is this is very hard to compute in general, because I've got a supremum over arbitrary states in the Hilbert space, and I've also got a limit as n goes to infinity, and there's various possible ways to arrange this. So in general, this is the sort of thing that quantum information theorists love because it's some very abstract quantity that you can prove theorems about but don't have a great handle on. But in a particular setup, which is bipartite unitary gates, so when the Hilbert space is just the product of A and B, you can make progress. And in particular, the finite dimensional cases where people usually prove theorems. So now, we think of the channel as just a unitary, so it maps some initial state, which is a joint state of A and B, to a different initial state, which might have some different entanglement structure. And in particular, time evolution does this. Time evolution is pretty unitary, and it might entangle or disentangle things. So now we define a quantity. Before I was talking about channel capacity. Now I'm going to define something called the entanglement capacity. And this is the difference, basically what I just said. It's the difference between the initial entanglement between A and B and the state, the entanglement between A and B after I've applied this unitary. In order to make that precise, I have to tell you what I mean by entanglement between A and B. And I have to say what I mean by difference. So we get this scary looking definition here. But the point here is I've got some entanglement measure En on some unentangled initial state. And then I apply a channel n t times, which is this operator pt, and I get the another entanglement measure in general. And then I take a supremum. And then I could be a little more general. Instead of starting with an unentangled initial state, I can start with some arbitrary density matrix. So far this doesn't look particularly nice, but this is actually a thing that people can prove theorems about. So again, these depend on choices of entanglement measure. So an entanglement measure basically has to obey some sensible things. So a product state shouldn't be entangled. It shouldn't change if I just do some change of basis in A and B separately. It shouldn't change if I just do classical operations. And it should, if I add one entangled qubit, the entanglement should go away. That's what these statements say. So there are a few obvious choices of entanglement measure. So there's the entanglement entropy, which is traced over log rho, and because we're computing information, we have a log x2 rather than a natural log. But then there's also some more physical ones, namely the entanglement cost and the distillable entanglement. So the entanglement cost tells me if I how many bell pairs do I have to spend to prepare a state using this channel? And so the distillable entanglement says if I've sent across the state using the channel, how can I break it down into bell pairs most efficiently? And it turns out for pure states, all of these things are equal, but for density matrices, they're not in general. Let me skip over the definition because this is what I just said, just made it a little more precise. So this is the rate at which bell pairs are consumed to produce copies of the state. In particular, if you need m bell pairs to produce n copies, then the cost of using the channel is m divided by n. And then there's a similar thing for the distillable entanglement where the channel, where basically I switch these things around. Okay, so the importance of this is now I can actually specifically write down a expression for channel capacity, where my initial thing is the cost of preparing the state, and the final gain is how many bell pairs I can distill it to. So this is the number of bell pairs that I get. If I consume some number of pairs, I apply the channel, and then I extract things from the resulting state. The reason this is important is because if Alice and Bob can communicate classically and they have some shared bell pairs, they can do quantum teleportation. And they can take any arbitrary state of a number of qubits up to this number and teleport them. So this is an explicit bound on the channel capacity. This is saying if I have access to this channel, then like at worst, like I can at least always do this teleportation procedure and get this number of qubits to the channel. So this is a very abstract number. Remember, it was double supremum, but this is a precise thing that I can calculate given a channel, and we're going to do it for the shorter scale. Okay, and let me just say quickly, another thing you can do, another thing you might care about with channels is, so channel capacity is this thing which tells you how to transfer information in the way I just specified. But another thing you can do is you can actually try to use the existence of the channel to tell you about the nature of the state that you've applied the channel to. So in particular, you could try to learn about what the nature of the wormhole was before the double trace deformation was applied. So if you remember a few slides ago, I showed you that in some cases, for some states of the wormhole, I'll be able to send a signal through after the deformation, and for some other states, this procedure will fail. So that by itself is already an example of the sort of thing I'm talking about. And just more precisely, an entanglement witness is an operator where if you apply it to one particular entangled state, it gives you a different outcome than if you apply it to every separable state. So this just differentiates like one particular entangled state from product states. This tells you, this answers the question, is it some entangled state, or is it not entangled at all?
Wait, are you saying it's particular to the Bob question?
Yes. So there is at least one density matrix such that you can do this. So this thing cannot exist for every entangled density matrix because that would distinguish all entangled states. Let me skip over this example. All right. So now, how do we define an actual channel for the traversable wormholes? So we start with an initial state, which is the thermofield double state. We've seen that we apply this deformation. So we're going to do the process of trying to send an excitation through. So first we're going to make some excitation at an early time. Then later, the double trace deformation will be applied. And then finally, we're going to check at the time it should be reaching the right boundary, whether there's an excitation there and what it looks like. So the final state here is just the composite of all these things. I've applied an excitation, I have a unitary time evolution up to the time I do the deformation. I do the deformation, and then I do some more unitary time evolution. All right, so this now, there is a map between an initial state and a final state, or in particular, there's a map between an excited initial state and a final state. So this thing defines a channel between the left CFT where I applied the excitation and the right CFT where I'm going to look for the excitation. And in particular, if I apply this excitation like at some point near the boundary, It's not just a channel between the whole CFT, it's a channel between boundary subregions. So formally, this is some map between some set of states, which I can create in the CFT, and states on the right. So again, we've got Alice and Bob. We think of Alice as making some states on the left, and Bob is looking for them on the right. So this is a channel. It's a channel between the Hilbert space of the CFT and the Hilbert space of a different CFT. So these are infinite dimensional channels. It's perfectly well defined, assuming you can say what this trace is, but we already need to do this when we do entanglement entropies and so on. But if we want to apply results directly from quantum information, it's more convenient to use finite dimensional channels. Luckily, this is a thing people have already studied for holography. Elmira, Damian Harlow had this notion of the code subspace. So this is just a finite dimensional coarse-grained version of Hilbert space. And the cost you pay for the coarse graining is that you get a little bit of nonlinearity. So to get this channel, we need some embedding between our coarse-grained space and the full Hilbert space. We're going to make this embedding, then we're going to do the time evolution, and then we'll map it back into the coarse-grained Hilbert space. So, for example, you can imagine you've only got one operator and you can apply it at a finite set of points. So now we've got d squared states in the Hilbert space. It's a nice finite number. And each of them has a CFT dual. And then we assume, as usual in holography, that these states have an interval background reaction. Sorry for moving a little further.
Go back.
Yeah.
I missed it. So, bulk operator. Okay.
Yeah, so I've got some bulk operator, which is dual to a C. Or I've got some bulk field excitation, which is dual to an operator. In the,
So we're latticizing the bulk.
yeah, I'm latticizing. It's not even really a spatial region. I'm just saying, let me define d squared states in the bulk. And depending on what like these choices of subregions are, this could be a latticization or not. And then what I do is I've got these d squared states. I associate each of them with a basis state in a d squared, in a d qubit Hilbert space. And then I've got two of them. There's one on the left and one on the right. So I've just got this map where for every state I associate the set of operators in the CFT. You need to make this one of these d squared states. And then to decode, I just pick a new set of boundary subregions and I check whether an excitation has moved. So again, depending on whether this is a real latticization or not, I can get weird results. So for example, if I only had two subregions, it could be that I've got some excitation and it passes through the wormhole, but it just goes out on some place where I haven't picked any of my subregions. So it will look like I have low channel capacity, but in fact what's happened here is I've picked a bad choice of subregions. So you can imagine, you know, if Bob only has the budget from the NSF for a certain number of detectors, he can make really bad choices of where to put the detectors and he'll get false negatives. Okay, so now we've just got a full channel where we do this mapping, we evolve, and then we do a decoding. And the way we do the decoding is we take our final state and we look at its overlap with each of the d squared discrete states we picked out. As I said before, because this is coarse graining, things get a little noisy. So in particular, if you look at the mapping of the thermal field double state itself, I haven't put in any excitation. Well, what's the overlap of the thermal field double state with a state where I've put in a little excitation? Well, it's a thermal state, so generically there's like some exponentially small thermal correlation. So all of these matrix elements will be non-zero. The only case when this won't be true is if the excitations are exactly on the boundary, because two different points on the boundary are an infinite distance apart, and therefore the correlation has to fall to zero. But in general, if I'm just putting some smeared operators in that aren't quite on the boundary, then this will be a little bit of a noisy map. Like the largest matrix element here will be the one with no excitations, but it will have support on other ones. Let me skip over this example. All right, so now I've defined a channel. I've defined an infinite dimensional channel, and I've also defined a coarse-grained finite dimensional channel. And now we want to do quantum information. So we imagine Alice is on one side and sending signals to Bob on the other side, and we want to see what we can learn about this.
Is there any limit to how big you can make alpha? It sounded like you just turn on H as long as you want.
Yeah, so the result I quoted for you assumes that the energy of the shock wave is small compared to the size of the black hole itself.
What does that do for alpha in terms of like,
Right.
sort of Planck size?
Yeah. So nothing is ever in Planck sizes. It's all going to be ADS sizes, basically. But if you remember,
We could answer later.
sorry. So alpha goes like this. So there's some exponential factor because the shock wave gets blue shifted as it goes towards the center. But then there's this H over L here. So you can imagine that like stuff gets pathological once like this exponential gets large, and that will make this rectangle large as well. And the way to think about this is if I've thrown in more negative energy than the black hole was to start with.
Sure. But it can be pretty big though.
Yeah, it can be pretty big. Yeah, this is definitely,
You can send the truck.
yeah, yes, right. And in particular, like I can shine a laser beam through it, there shouldn't be a problem. Now I've just written a bunch of times. Okay. Okay, so we've got this infinite dimensional channel and finite dimensional channel. And now, because of the power of holography, array holography, we can actually try to compute channel capacity. So if you remember, I got this bound when I was talking about quantum information. Channel capacity is bounded by entanglement capacity. This is asymptotic entanglement capacity, and it has to be at least as large as one-shot capacity. And it turns out in many cases, Charlie Bennett and collaborators managed to show that, in fact, this thing is exact. So doing it once, there is some way to apply the channel once, which is as good as you will ever be able to do by applying it a whole bunch of times. Okay, so what's this one-shot capacity? Well, the thing what we're going to exploit is the one-shot capacity has to be at least as large as like physically shoving some bell pairs through the wormhole, or halves of the bell pairs through the wormhole. And this is the thing where you can estimate using holography. Again, basically just by counting. We've thrown in some negative energy shock, which will force the wormhole to be open. I can only pump in enough positive energy such, like, once I've pumped in enough to undo the shock, and since I'm in the no back reaction limit, I've just got the black hole state, which is not connected by a traversal wormhole anymore. So, you might say, all right, I can just keep sending really low energy signals through the wormhole, but in fact, the wormhole only has a finite width, so in order to actually get a signal through the wormhole, its Compton wavelength has to be smaller than the size of the throat. Otherwise, it doesn't fit through. So that says that alpha times L has to, well, this is the size of the wormhole, alpha times L. Remember, alpha was the window, and that was dimensionless units, and then ADS gives you the dimensional factor. So that means that each signal has to have an energy corresponding to this Compton wavelength. And so we can saturate, so now I'm sending pulses with positive energy through, and each one of these is going to be a little mini shockwave basically with positive energy, so it will move the horizon outward a little bit and it will shrink the size of the throat. So the best you can do is sending all of the signals right at the same time, so they all feel this as large a throat as possible. Saturating the bound is just saying n max goes as the energy of the shock over the energy of each signal, which scales as alpha times L times E. So this is sort of the best you can do. It is the best you can do. Now, I said this is something where we threw a whole bunch of information through the throat, and it closes up behind us. So we've thrown enough energy to negate the negative energy shock. So this is sort of a very non-perturbative thing to do, but we're in GR. So with it's fine, I just don't really have any quantum control over this. So Maltesian and Stanford Yang also considered information transfer bounds, but they were interested in the probe approximation. And in fact, what this is telling you is most of the information you can transfer is information that will cause stuff to shrink a little bit, so you're far away from the probe approximation. So we've done this process where we opened up the wormhole, and then we threw in enough stuff to close the wormhole behind it. Okay, so this is a computation, this is a bound on channel capacity in the case that the channel is describing. This is a channel corresponding to a traversable wormhole. In the last minute, let me tell you about entanglement witnesses. So we just said that if we want to send as much information as possible, it's a one-shot thing. We throw it in all at once. On the other hand, though, we might care about the structure of the wormhole itself. If we're trying to do quantum gravity as opposed to just conveniently having this channel go out. And so you might imagine that you want to send multiple separate signals through. So for example, say Alice thinks there's going to be double trace deformation that's going to be performed, but we don't know how big double trace deformation is. So Alice can send signals in some interval, and then ask Bob to report back to her we send the signals, each of them has a slightly different frequency, so it encodes like, this is the first pulse I sent through, this is the second, and so forth. And we see what the first pulse that gets through is and the last pulse. And there's this exponential compression here because things get blue shifted as they reach the boundary. So this thing is a partial entanglement witness which bounds the size of the wormhole fringe. It's a little bit more complicated because, as we've seen earlier, we don't know that we're in the thermal field level state by itself. So in fact, we're not actually bounding the size of alpha. We're bounding the size of alpha minus this V naught, which is this unobservable feature of the geometry. And also, we have to space pulses exponentially close and the pulses back react. So we've got this complicated trade-off between the energy of the pulses and the spacing. So the experimental protocol you would do for something like this is the usual Bayesian thing. I have some guess, I've got a prior for what this quantity is, and I've got some resources, how many pulses I can send, what the total energy is, over what time, that sort of thing. And I'd like to choose it so that I learn the most information, which in Bayesian terms is just a posterior distribution. I want to minimize the entropy of the posterior given the prime. And in particular, all of these signals are entanglement witnesses, and I can basically do wormhole tomography using this. I can learn about how long the wormhole is open, and if I can actually resolve the physical size of the wormhole, I can send it at slightly different angles. I can learn about the physical size of the wormhole. Also, there's some redshift factor that comes from sending a pulse to the wormhole. If I know what the frequency is when I started, I can measure off the total redshift, and I can learn about how long it took to go through the wormhole. So people care about the lengths of wormholes in this complexity story, and this is sort of another way to do it. All right, in the last negative 1 minute, I will conclude.
So I delayed you.
Okay, cool. All right, in the last however long it takes, I will conclude. So what have I said? We've got this process here, which is I want to send signals through a traversable wormhole. I told you a way to describe this as a quantum channel between the CFT boundaries. I mostly described it by pointing to things on a Penrose diagram, but since I know how to construct the thermal field double state using a path integral, and I know how to apply the deformations to this, I can pretty much straightforwardly construct this in the CFT. I know how to draw the geometry to do it. The actual replica integrals might be a little hard, but I can definitely write down the formula, which if you could do the integrals would give you the right answer. I also showed you how to construct a finite dimensional coarse graining of this, and now instead of a map between two CFTs, it's a map between finite dimensional code subspaces. And then I told you that we can really think of these excitations in the bulk description as just sort of physically going through the wormhole. It's not, from the boundary perspective, it's teleportation, but if there is a bulk description, I really started with some photon wave packet on one side, and I got it to the other side. So what does this tell me about quantum information? Well, for an arbitrary channel, I've got it's very hard to compute the channel capacity because there's this supremum that I don't really know what to do. But because I have this gravitational description, there's a way to bound it pretty precisely. I know that this channel is limited by the size of the shock wave I used to construct it in the first place. And you might hope that there's other information theoretic quantities that you could deal with in a similar way, and that's interesting further work. And we also considered not just channel capacity, but using the signals to learn about the wormhole itself, using the fact that the signal makes it through successfully as an intact mechanism. All right, so then more generally, what have we done here? We got some non-trivial results about channels because a bulk description existed. In particular, from the CFT perspective, what happened? We put in some very sharp excitation, and then we turned on time evolution with this double trace deformation. Well, what's CFT evolution for a large Ncft? It looks like this very fast, as fast as possible, maximally chaotic diffusion throughout the system. I don't know how to describe it at all in a local way. But then at some other critical time, it moved over to the second CFT and got localized again. So this is sort of a miraculous thing. This has been calculated exactly by Hamiltonian and collaborators in SYK. But if you've got this wormhole description, we know it has to happen for a CFT of arbitrary dimension. Where this is basically, we know this has to happen because there's a bulk description. So you might hope you could flip this around and have a quantum information theoretic definition of holography. If I have an arbitrary channel, I don't expect anything like this to happen ever. Basically, if I do have a channel which transfers a localized excitation to a localized excitation in this way, that means there's got to be a description in which I can think of this excitation as actually physically moving from some bulk property in some way. So it would be interesting, if possible, to make this precise, because it would sort of give you a diagnostic without having to appeal to gravity explicitly of when a bulk description exists. Great, thanks.
This whole story was in 3D, right? In this 3D, where the issue of two CFT arrivals.
So the explicit results I quoted for you use